Hey, we have motion here. Hey, we have motion. Okay, so
May I give an introduction?
yes.
Okay. Einstein's general theory of relativity addresses gravity not as a single force, but as the result of the warping of space-time caused by the presence of mass. It's what all of us are all mass. Okay, so it was long predicted that extremely massive objects that move would cause gravitational waves to propagate through the universe, like the waves generated by a stone when you drop it into a pond. Well, these were finally detected in 1974 by the Laser Interferometer Gravitational-wave Observatory, LIGO for short. Tonight's guest speaker, Kimberly Burtnyk. Burtnyk, sorry.
That's okay.
Who works at the facility and she's offered to explain how on earth this works. It's incredible. She's also generously donated our honorarium for the NJAA. Well, everyone, please welcome Kimberly.
No. Okay, can you hear me?
We can hear you.
Okay. I will share my screen and then I will introduce myself. Is that okay?
Absolutely.
Okay, let's get
We're
this.
going to hold questions until after her presentation, before she does the tour of the facility. Okay?
From the beginning. Okay, can you see my slides?
Yes.
Okay, good. All right, so my name is Kimberly Burtnyk. I'm the LIGO Laboratory Technical Editor and Science Writer / Science Communicator. I've been with LIGO for 11 years, just over 11 years now. My background actually is in astrophysics. I have a degree in astrophysics. I have a graduate degree in science communication as well. And yeah, through a long circuitous path, ended up at LIGO, and just 15 months before our very first detection is when I arrived. So I had really good timing. I am really excited to talk with you guys today. I'm glad that you have time to learn a little bit more about LIGO. We just had our 10th anniversary of our first detection, so the timing is really good to kind of talk about this. So let's jump in. Oh wait, now I'm not seeing my slides. Let's see. My screen is stuck on the first slide.
Did you hit play?
I did, but let's see.
There you go.
Yeah, it's not letting me click through though. Oh wait, maybe it is.
Oh,
here we go. Okay, now I got it. Okay. So, you know, for most of human history up until very recently, everything we learned about the universe came from electromagnetic radiation, in other words, light in all different types of wavelengths. So the pictures over here are images of part of the Milky Way galaxy, the same region of Milky Way, but taken in different wavelengths of light. And so you see that each time we observe the universe in kind of a different way, or a different messenger in this case, we learn something different about what's going on. So as John said, though, there was this other thing lurking in the universe that we were never able to observe, but we were hoping to. And actually, it wasn't, it was the Hulse and Taylor in the 1970s that were the first to indirectly measure gravitational wave by looking at the decay of the orbit of two stars called neutron stars. They won the Nobel Prize for their work, but LIGO we didn't make our first physical sensing of gravitational waves until 2014, or 2015 rather. So yeah, we're just 10 years into the actual physical touching, in a way, of gravitational waves. So what are gravitational waves? We had a little intro already. They are perturbations in space-time made by everything that has mass in the universe that accelerates. So acceleration can also mean planets orbiting stars, stars orbiting each other, things that are kind of moving around each other, or things that explode. Supernovae are massive stars that at the end of their lifetime, they blow themselves to smithereens. Spinning neutron stars. Neutron star is another kind of potential end stage of a massive star, much bigger than our sun, 10 to 25 times size of our sun, will turn into something called a neutron star at the end of its life. If you've heard of pulsars, pulsars are neutron stars that are emitting beams of radio waves. And so we call them pulsars because as they rotate, the radio wave kind of cone, the beam that they're sending out intersects the Earth at some point, and we can pick those up with radio telescopes. If a neutron star happens to have a tiny little bump on its surface and it's spinning, that would be enough to emit and kind of kick off gravitational waves. And then we have things like orbiting and colliding neutron stars, again, or black holes. And the black holes are the things that we are detecting. That's what LIGO has detected so far. The things that are kind of smashing into each other. We have not yet detected a supernova or just kind of a lump on a neutron star, but we have detected neutron stars colliding with black holes smashing into each other, and at least one case of two neutron stars colliding. And I'll talk a little bit more about that later when I talk about some of our kind of exciting discoveries. So as we already was introduced to you already, thank you, John, gravitational waves were predicted by Einstein in general relativity. They propagate at the speed of light, and they squeeze and stretch space as they go. And so this kind of video that you're seeing here, some call it the windsock. I call it kind of a giant space worm. That is a way of imagining or kind of visualizing the effect that a gravitational wave has on a region of space. And in this case, it would be as if this was, if that were a long tube of space, observatories or detectors connected in this way. If a gravitational wave was passing, that's kind of how space-time itself distorts. And the important thing to note here is that gravitational waves are a completely different phenomenon from light, from electromagnetic waves. And one way of looking at it is they are as distinct as sight is to hearing or hearing is to sight. So, light waves are waves, sound waves are waves, but they're completely different phenomena. So sometimes I say to people, imagine we were a species that only had eyes and we learned everything we knew about the universe by just observing light in different wavelengths of light. And then somebody invented an ear and you realize there's a whole realm of observation and kind of things happening around us that we never had access to because we couldn't sense them in that way. And so that's what LIGO has really done. It's kind of opened a completely new sense, a new way of observing phenomena and processes in the universe that just didn't exist before. And for very good reasons. And it's an exceedingly difficult thing to do. So again, that means if we can observe these things, we're going to learn a lot more about the universe than we'd ever known before. In the same way that every time we've used a new wavelength of light, we can kind of see something different. But LIGO and gravitational waves are accessing a previously wholly inaccessible part of the universe. So let's look at kind of the anatomy of a gravitational wave. Let's see, off in the distant universe, we have a couple of black holes. These were massive stars that at the end of their lives turned into black holes, and they've been orbiting each other for millennia. And they smash into each other, and they emit a burst of gravitational waves. Now, when they emit the waves actually propagate in all directions, just like a flash bulb of light. The light goes off in all three dimensions all over the place. Or sound kind of is emitted in all directions. Gravitational waves are emitted in the same way. But if we could just look at this wavefront, one kind of propagating wavefront of a gravitational wave moving in this direction, and we'll bring back our little windsock here. This is kind of what it would look like. Again, if you imagine that a wavefront of a gravitational wave from the distant universe, we're moving through this kind of object or, space creature from one side to another. This is how it would physically respond. Now, this is greatly exaggerated because the effect is really, really small. But this is a physical phenomenon that actually happens. So it looks pretty complicated. You see all the things moving, but if you just kind of pay attention to that leading edge there, you notice something. We could make a detector that was a circle and kind of track how the circle squishes and stretches over time as the wave is passing. But if you just look at that leading edge, you notice that all that's really happening is this kind of oscillation up and down. And so instead of having to make a circular detector, all we really need is an L-shaped detector. And that's why LIGO is the shape that it is. So just a little things to point out here. We are here, I'm sitting in this building. This is the Hanford Observatory where I'm based in southeastern Washington state. We are in a shrub steppe environment, so it's kind of a desert climate out here. And this is what we call the corner station, where the laser is emitted. I'll get into the details in the next couple of slides, but just so you have a sense of scale, the instrument has two arms at 90 degrees to one another. Each arm is 4 kilometers or 2.5 miles long. So again, I'm in this little building here, and then off into the desert go these two arms. It is the world's largest laser interferometer, and it's also the most sensitive measuring device that human beings have ever created. So a little bit about LIGO Laboratory. So LIGO Laboratory comprises 2 detector sites. So there's this one where I am in Washington, and then we have an identical facility in Livingston, Louisiana, and we operate in unison as much as possible, environmental factors notwithstanding. And that's really important to our, how we make our discoveries and how we can kind of figure out where things are on the sky. That's why we need the 2 detectors to operate. And the map over here just shows us, kind of rough locations of the facilities. So Livingston, Hanford's up here, Livingston is down here. And we are managed primarily by Caltech, the California Institute of Technology. So I'm actually an employee of Caltech. Everyone who works for LIGO is a Caltech employee. And MIT, Massachusetts Institute of Technology, which you all know, is also a partner institution. The other thing to point out here that this little, this shows is our detectors are deliberately built 3,002 kilometers, very precisely, apart. And that's because we know the gravitational waves travel at the speed of light. So the light travel time between the 2 facilities, the maximum light travel time between the 2 facilities, if a gravitational wave were to pass through one and then directly in a straight line through the other, is 10 milliseconds. That becomes important to how we verify our discoveries and how we can kind of rule things out. If Livingston detects something that looks like a gravitational wave, and then more than 10 milliseconds later, we detect something that kind of looks like a gravitational wave, we just ignore it because it's not physically possible. So that's an important consideration, the distance between the 2 facilities. Okay, that's just a little bit of business work. Now, how does LIGO work? We are a laser interferometer, which means we take a single laser beam in this building, not far from where I'm sitting right now. And one thing that a lot of people do ask is, do we turn the laser on and off or on? No, the laser is on. When we're observing, the laser is on all the time. And that's because we split the laser beam up in this building. There's a beam splitter, which is kind of like a partial mirror. It sends half the light down one arm, and then it sends the other half of the light down the other arm. It actually reflects back and forth. There's mirrors at the end. Sorry, these are what are called end stations at the end of the arm. So the laser starts here, it travels 4 kilometers down here, it bounces off a mirror at the end here, and then it returns. Instead of returning directly back, there's actually a couple more mirrors in here that enable this light to circulate back and forth about 300 times in each arm before we extract the light. And so each kind of photon travels about 1,200 kilometers. So I can't do the math right, 750 miles, I think, roughly, from the time it starts here, runs up and down the arms, bounces around, and then it comes out of the instrument, and we look at it with a photodetector, which is a device that measures kind of the intensity of light that's coming out of the instrument. So what we do is we split the beam up and then we recombine the beams. And that's why we're called an interferometer, because when you recombine light beams in this way, the waves of light will either, they'll interfere with each other. They'll either constructively interfere, you get a brighter light. They will destructively interfere, where the light will cancel itself out. Similar process to how you might see waves in water. The waves behave the same way. But in light, you either get a brighter light or no light. And we look for this interference pattern, basically a flicker of light that comes out of the instrument. That's what we're looking for. So if we turn that into a little video here, I just overlaid, this is just a very simplified version of what I'm talking about. So let's back up a little bit. Gravitational waves, we remember with our little space worm here, cause space-time to actually physically squeeze and stretch in this kind of orthogonal or at these 90-degree angle way. We use a laser to constantly measure the lengths of the arms, or how far away each of these mirrors is. And we, again, the light comes out, it gets split here, it gets recombined. This here is what you'll see as a photodetector. What happens here, what the photodetector senses, tells us what's happened in the arms. And so in principle, it's kind of a simple device. Obviously, it's a pretty sensitive, complicated thing. But thankfully, thanks to the equations of general relativity, we can predict the type of signal that the photodetector will see. And so we can compare what we actually see with what our predictions are. And then we can say, oh, is there something that kind of matches what we think, something that might have been a gravitational wave. And I'll come back to that in a minute. But let's just play this video for a second so you can see what I'm talking about. I think I need to ditch my laser pointer. Oops. Let's see. How do I play this guy? Nope.
You hover back down there. Oh, left. Next one to the left. There you
This
go.
guy? No, I'm trying to play the video here. I'm trying to remove my laser pointer. Oh, there we go. Just disconnect. Okay. So this is what I've been, yammering on about. This is kind of how it appears in video. So the laser comes out. It goes through this photodetector, or sorry, this mirror here that splits it in two. You'll see that happening. It travels all the way down, 4 kilometers down the arm, hits a mirror at the end. Actually, again, bounces back and forth about 300 times. Then we recombine the beams and we see what comes out. So we see, in this case, what you're seeing here, the beams are completely canceling each other out. We generally hold the instrument in a state so that when the beams are recombined, they totally cancel each other. So no light comes out of the instrument. That's kind of the stable state when we're not sensing any odd gravitational waves. But if something were to change the distance of between the mirrors here, then the light here won't combine so nicely anymore. So you're going to see that this is an exaggeration. Say a gravitational wave is passing. You note how when one arm gets longer, the other arm gets shorter, and they oscillate back and forth. That's how our instrument responds to the gravitational wave. And so as that happens, you see in the corner here where the beams are remerged, that they kind of move over and through each other. And as they do that, you either get a bright light or you get no light. And it essentially, we get like a flicker of light that comes out of the instrument. The nature of the flicker of light, it can change in intensity, it can change in the frequency, and those are kind of the two main things that tell us what's happening in the arms. So lots of things can cause the arms to kind of shake, like earthquakes and trucks driving along the road and wind, the tide, the moon, you know, can cause all of these things to, can cause the mirrors to change their positions. We have thousands of feedback mechanisms that prevent all of those noisy activities from basically affecting our mirrors. And that's kind of some of the engineering that I'm not going to talk about, but if someone has questions later. But our main job is to make these mirrors feel like they are floating in space, like they don't feel anything, any vibrations coming from the Earth, so that if they move, we know the only thing that could possibly have caused that is coming from off of the Earth. And so that's how we look for gravitational waves. And again, just to point out that we can predict what those look like. So this is kind of the extraordinary thing. Using this method, we can measure an arm length of change that's a few, you know, it's a fraction the size of an atomic nucleus. And when you divide that number by the 4-kilometer length of the arm, it means that we can sense a change in length, which we call strain, of about 1 part in 10 to the 22, which is a mind-boggling number. Don't even try to think about it. But since we're astronomers here, here's kind of a cool way of thinking about it. It's like if we could measure the distance to Proxima Centauri, which is the nearest star to our sun, it's about 4.2 light years. It would be like us being able to see it change in distance by the width of a human hair.
Yes.
That, you know, when I kind of figured that out or learned that little fact, we've had different ways of explaining this to people. And to me, this really kind of the mind-boggling nature of this just kind of hit home, because when you think about how far 4.2 light years is, and that's the level of precision that our instrument is achieving right now. So how do we then do that? You know, where these signals are so tiny, how can we possibly know, you know, that we have sent something? Like I alluded to, we have mechanisms that remove Earth-based vibrations from the instrument. So, you know, we're only hopefully seeing what's coming from outer space. That's the ideal situation. It doesn't always turn out like that. But then, you know, what do we do with the data? So because the laser is on all the time, the signal is constantly being, you know, the laser's on all the time, which means light is constantly coming out of the instrument as well as it's bouncing around. And so in real time, we're basically sending that stream of data, all those flickers of light, get sent through something that we called a template bank. The template bank is, last we checked, about 300,000 sample gravitational wave waveforms. And these were generated by punching all kinds of different numbers into the theories of general relativity. And it spits out potential, you know, shapes of gravitational waves. So I think there's something like 7 different variables, but some are how far away, you know, you can change the distance of the wave, you can change, or the distance of the source, you can change the masses of the sources, you can change the orientation of the sources, you can change the spin of the sources. And so we made about 300,000 different versions of these kind of sample theoretical gravitational wave shapes. And as the data comes out of the instrument, we send it all through these filters that look for one of those shapes, or at least something that's kind of close to one of those shapes. You know, we're never gonna, there's an infinite number of shapes that you can make. So we look for something that's close. And so if a segment of data resembles one of these templates, it gets kind of, you know, flagged like, oh, this might be a gravitational wave. And we do some further analysis on it. And within a few minutes, we can determine whether or not it was a gravitational wave. And I like this kind of toy off to the right here as an example. I remember this when I was like, you know, really, really young. So you can imagine the ball here is our template bank except instead of what, like 5 or 10 different shapes, there's 300,000 different shapes. And these little blocks would be our little waveforms that you're trying to, each one that comes in, you're trying to fit into one of these shapes. And so we have some pretty powerful computers that do this analysis in real time, constantly as the data is streaming out of the instrument, looking for something that looks like a gravitational wave signal. So, okay, we can do that. Let's get to some of the fun stuff since we're an astronomy group. What have we actually found? So we're kind of lucky. We recently have published some new results. And most importantly, every time we're currently in what we call our 4th observing run of the advanced detector era. And that era started in September of 2015, right when we made our first detection. And we've gone through 4 different observing runs. An observing run for us means we will operate the instrument 24 hours a day, 7 days a week for some months. And then we'll shut down, make some upgrades. And then we'll operate for a little bit longer time. And then we shut down, make some more upgrades. And so we've done this 3 times. We're currently in our 4th observing run that started in May of 2023 already. We're going to wrap up this run in November of this year. But this is kind of a fun graphic. And all of these, I can send you resources. You can see all of these online too. There's some, Northwestern University generates these so-called masses in the stellar graveyard charts. But I'll show you kind of our progression over the course of our 4 observing runs, which amounts to like 49 months, about 4 years of actual observing time. I'll show you what we have detected. So this first graph, I will get my laser pointer again. What you see down here, these yellow guys are neutron stars that are known from regular astronomy, from electromagnetic astronomy. These red dots here are black holes that were previously observed and discovered through electromagnetic astronomy in different ways, either, radio waves, X-rays, all kind of different ways of light, different wavelengths of light that we've used to discover, a handful of neutron stars and a handful of black holes. And so the red and the yellow here, let me move my thing up here. There are, before LIGO came along, there were only 106 known either neutron stars or black holes. And that took about 60 years worth of observing in astronomy to make this discovery, to discover these objects. LIGO, and the chart that I'm going to show you, we have now this chart, which is what we just generated from our 4th, the GWTC is Gravitational Wave Transient Catalog. It's basically the catalog of the discoveries that we have published and that's now accessible to the public or the rest of the scientific community. So in 49 months, the chart's only going to show you 176 events. The blue guys are LIGO events. But when I counted yesterday, we are up until yesterday, we now have 330 candidates. We call them candidates until they have been fully vetted, and then we release the data to the public. But the first ones that you see here are what we would consider actual events. So some things to note that are kind of interesting is that, oh, this isn't working. Let's try out, maybe because this guy, it must be this thing. Okay, let's try it. Let's see. Changing. Okay, here we go. Okay, so this is our first and second observing run. We're starting to fill in all of these blue things are things that LIGO has discovered. Our first 3 observing runs. And then what we just released a few weeks ago was this list.
Oh.
And again, this is only 176 detections as of, and that comes to, I forget what date that is. That's like sometime last year in 2024 is what that number comprises. But when there's a list you can look at online, And yeah, I've been kind of tallying and keeping a tally. We now have about 330 candidates. So this is going to get extra crowded. One thing to interpret this graph is each of these kind of arrows, these lines here, is considered a single event in LIGO. The two lower objects, there's 3 objects in each of these lines. So if we start right here, these are the 2 orange guys are neutron stars. What we observe is like 2 objects colliding into one another and then the resultant kind of remnant object. So each of these lines is actually 3 objects. The 2 that we measure and that we can say, oh, this was a 7 solar mass black hole and a 12 solar mass black hole that smashed into each other and made a 19 solar mass black hole. So individually, there are 176 lines here. So if you multiply that by 3, then technically LIGO is discovering like thousands of black holes that had never been seen before. The other interesting thing to note, though, is kind of the masses of these things. So the electromagnetic astronomers were only kind of seeing these lower mass. The vertical scale here is how many times the mass of our own sun that these objects are made of. So yeah, it's kind of interesting to see, neutron stars are lower mass objects, black holes are higher mass objects, but even the EM folks, weren't really seeing a lot in this upper range. So LIGO is starting to fill in the gap in the universe of what are these objects out there that are much higher masses. And some of these here, I just sorted these from the low mass to high mass. These aren't sorted by date or anything, but just so you can kind of see the progression of like the variety of species of black holes that we are detecting. This one up here, right at the very end, we had a special announcement about that one a couple weeks ago. It's the heaviest kind of black hole stellar mass, so-called stellar mass black hole that we have seen. We distinguish between something called a stellar mass black hole, which are things that we think are generated either by an individual star or now we think by successive mergers of black holes. So a massive star ends its life, it becomes a black hole. It happens to be near another black hole. They smash into each other and they successively make larger and larger and larger black holes. Just like if you have like bubbles merging together, you can make a bigger and bigger bubble. And astronomers don't know how to make black holes of this scale over 90 or 100 times the mass of our sun with a single star. And so this is kind of opening up a new realm of astronomy where we don't really understand where these objects come from. We're kind of presuming that they're these successive mergers because we see smaller ones turning into bigger ones as they go up the scale here. And some of you might have heard of things called supermassive black holes. Those are a completely different thing. Those are giant black hole type objects that live in the hearts of galaxies. Almost every galaxy, we think, has a supermassive black hole in it. And supermassive means millions or billions of times the mass of our sun. So, we're not seeing those types of things. We are seeing these things that we call stellar mass black holes. Because we think one way or another, they have formed either by a single star or by successive mergers of black holes. So just kind of breaking down, we have 330 detections or candidates. Again, it's considered a candidate until we totally vet the thing and we're certain that, we have a high level of certainty that yes, this was for sure a gravitational wave event. And that breaks down into primarily binary black hole mergers. So 2 black holes that had been orbiting each other that smashed into each other. These ones that are kind of these ranges, the range is there because there's some uncertainty in the masses of one or both of the objects that were involved. So we think we have 2 to 3 binary neutron star mergers, 5 to 6 mergers of a neutron star and a black hole. And then 3 to 4 so-called mystery mass gap objects. And I'll touch on that a little bit later. The other thing to note, why are there all these binary systems? Well, probably about half of the stars that we see in the sky are actually binary systems. There's 2 stars in orbit around each other, if not more. And so, we're not surprised that we're seeing, that's one of the reasons why astronomers and physicists expected to see things like merging neutron stars and merging black holes. Because when you have stars that have formed and have lived their lives in pairs, and then they die in pairs, and we know that as they orbit each other, they're giving off gravitational waves, that causes them to get closer and closer and closer together until they eventually collide. So that's why, you know, we're seeing these binary systems. It's just part of the nature of the universe that you see stars that are, you know, have lived their lives as companions in pairs. So some highlights, you know, we have our first historic detection, which is 10 years ago now. We had a big celebration near 2 weeks ago. Our site and Livingston and around the world, some of our people who are part of our greater collaboration, we all had, you know, big public events. We had Barry Barish, one of our Nobel Prize winners, was speaking here at LIGO Hanford, and we had special tours. So it was really a big deal for us that it's been 10 years since this whole new realm of the universe has opened up. So, you know, it may be old news, but it's still a big one. It was the first. It was a beautiful detection. It was the very first binary black hole merger. You know, these systems had kind of been theorized. Nobody really knew if they existed. Well, you know, now we know that they do. And we also obviously then confirmed that these systems do end up colliding with one another, that the black holes will actually collide with one another. In terms of like the energy that these things give off and why it is that we can detect these things so far away, this first detection, one component, one of the black holes was about 30 times the mass of the sun. It smashed into another black hole that was about 36 times the mass of the sun. And when you put those together, you think it should be 66. Well, when we looked at the final object that resulted, our estimate was about 63 times the mass of the sun. And that means that when these things smashed into each other, 3 solar masses worth of matter or of black hole mass, you know, black holes aren't matter. We're not sure what's going on in black holes yet, but 3 solar masses worth of black hole was converted instantaneously into pure energy. And that's what causes these, you know, vibrations in space-time. And putting that another way, it's about 50 times the power of the entire visible universe in those 0.2 seconds. This event was only detected sensed in our detector for 0.2 seconds. So literally the blink of an eye, this thing just blew past us. Our estimate was about 1.3 billion light years away is where this thing happened. So the waves had been traveling for over 1 billion years by the time they reached the Earth. And of course, most importantly, it verified that LIGO works. And that was a really, you know, obviously a really watershed moment for us. A couple years later, I think we had what I still consider to be our most scientifically rich detection. I think others do as well. And that was our first binary neutron star merger. And one way that we, you know, I talked about the templates and how we can determine, you know, that each signal is going to be unique because each system of gravitational waves or each system of black holes around each other or neutron stars and black holes, they're all, you know, they're all completely unique systems. They all have different masses. There are, you know, different properties. So no 2 signals are going to be alike. And that's how we can kind of make this bank of 300,000 plus sample templates. And that's one way that we can distinguish between, say, a black hole merger and a neutron star merger. So in this case, I kind of, I took the image from this chart down here, and I just kind of jankily with the PowerPoint squished it down to be of the same scale as this neutron star merger. So the neutron star merger, we actually sensed this in our detector for about 100 seconds. This is just showing the last 30 seconds or so of what we could actually sense in the instrument. And so this shows the difference in characteristics between a black hole merger, which is this tiny little blink of an eye, and a neutron star merger, which takes a lot longer. It spends a lot more time in our kind of sensitivity range before the objects finally collide and merge into one another. So that's just one way of illustrating, you know, the different types of signals that we're getting and how we know what something is and how we distinguish between them. So we had our first binary neutron star merger. And that became important because it was also the first one that was detected, what we call a multi-messenger event. So there was, we share our data in real time with some partner institutions around the world and scientists around the world. And some of those are gamma ray observatory people. And so when we had this detection, we send out an alert that says, hey, you know, at this time, everything's time stamped very precisely. We had a gravitational wave. And in this particular case, 1.7 seconds after the gravitational wave arrived, there was a gamma ray burst detected by 2 orbiting gamma ray observatories. And so that made astronomers and scientists around the world really kind of pay attention, because they're thinking, what, you know, this can't be a coincidence. And it turned out that it was not. So this was the first and to date only time we have seen a gravitational wave, both in gravitational wave kind of frequencies and modes, and also in light, in this case in gamma rays. Because we could do that, and this event was observed by the Hanford Observatory, the Livingston Observatory. We also partner with a facility in Italy called Virgo. It's a bit smaller than us, but there's a bit of a story with Virgo. Virgo should have seen this event. It was powerful enough that it should have been within reach of their detector. When they looked for it, they didn't see it. But it turned out, something that I skipped over, each of our instruments actually has blind spots. Depending on the direction that the wave is coming from, the arms might react in a way that we don't get an interference pattern coming out of the instrument. And it just so happened that when we looked at the sky map that each of our detectors can generate, so Hanford can say, okay, it came from this region of sky. Livingston says it came from that region of sky. And when we overlaid that with Virgo's blind spot, everything overlaid really nicely. So that's an important lesson. The fact that Virgo did not see this event was absolutely critical to us actually localizing the thing on the sky. So here's a nice map that shows kind of the result. This big swath here is one of the gamma ray facilities, observatories, kind of their map, if you could call it. The signal came from this part of the sky. It's huge, right? This is like a whole, you can imagine the Earth at the center of this sphere. This is a giant part of sky. Fermi was this kind of blob here, a little bit more narrowly localized. And then LIGO was the light green, just LIGO Hanford and LIGO Livingston. We kind of made these banana shapes. And then when we included Virgo and Virgo's blind spot, and we overlaid all of these different sky maps, we ended up with this pretty small region of sky. And it turned out within, I think, 11 hours, this SWOPE telescope, optical telescope in Chile, they were imaging every galaxy that they could find in that patch of sky. And pretty quickly, they spotted this new, looks like a nova in this galaxy called NGC 4993 in Hydra. So it's pretty low for us. My husband and I have actually seen this galaxy in our giant 22-inch Dobsonian telescope. It was probably easily one of the most challenging things that I have ever observed. It was not much to look at, but it was still fun to know that, you know, photons from this galaxy were like hitting our eyeballs in that moment. So, you know, we didn't see this event. This was like sometime after, but we did see the teeny faint smudge of this galaxy. So kind of putting that into a different perspective, Cardiff University makes these beautiful sky maps. And so this is the tiny little region of sky that we were able to narrow down by using both the gravitational wave maps and the gamma ray maps. So this is just kind of a nice picture. This became the most studied astronomical event in human history to date. It still is. There's a nice animation here that shows it the first observation on August 18th in optical wavelengths, and then slowly fading over the next 11 days. It answered a question about what are these short gamma ray bursts? You know, gamma ray observatories have seen short gamma ray bursts for, you know, a number of times, and nobody really knew what they were. There were theories that it could be something like neutron stars smashing into each other, something called a kilonova. And so this coincided with a short gamma ray burst. So we know now for sure that at least one source of short gamma ray bursts is colliding neutron stars. Because we had light to compare with the gravitational wave signal, arrival of signal, we were able to estimate the Hubble constant, which is the rate of the expansion of the universe. There's still some disagreement depending on how you make this measurement, but LIGO, using LIGO's data, it fell within range of both of those kind of primary, main estimates. So it was consistent with the electromagnetic or light-based estimates of the Hubble constant of the expansion of the universe. And it verified that gravitational waves do in fact travel at the speed of light, and that was predicted in general relativity. Another huge thing that came out of this was that it transformed the periodic table for us. So all of these things in orange, before this event, anything in orange here, and these numbers, we meaning the scientific community, didn't really know where these heavy elements came from. So when I was learning, when I went to school and I was studying astrophysics, I was taught all of the heavy elements, everything over iron comes out of supernovae. Well, that's an exploding star, a massive star, blows itself up. There's this process called nucleosynthesis when that happens, and it makes all these different heavy elements. Well, it turns out that was not entirely a lie, but not entirely the truth either. And in fact, we didn't know where a lot of these really heavy elements came from. We see them on Earth, but we don't see processes in the universe that kind of generate these materials. We can study nebulae and processes in the universe, and we can, look at what they're made of. And we weren't seeing the abundances of these types of things until this event. So when astronomers were looking at it after it happened, and they're looking at the spectra, which tells us what the aftermath is, what is the material that's kind of generated, all of a sudden they started seeing evidence and traces of all of these heavy elements. So now we also know that at least one good source of all these heavy elements that we see on Earth has to be colliding neutron stars. And that includes things like gold and platinum, which, many of you are probably wearing on you, earrings, rings, whatever, at the moment, came from, at least in part, came from neutron stars that smashed into each other, who knows how many billions of years ago, potentially. And in terms of the numbers, there were estimates of about 16,000 times the mass of the Earth worth of these heavy elements that came out of this one event, including, rough estimate. These are kind of loose estimates, but about 10 times the mass of the Earth in just gold and platinum alone. So huge, huge discovery this was, something that we didn't understand at all about the periodic table, that this single event has helped us to understand. Unfortunately, it's the only one of these types of events that we have seen. And so, the more of these that we do observe and can study in this same way, the better we'll be able to kind of understand how much of these elements are actually generated in these types of events. But most certainly, there was a lot of this stuff that came out of these events that we didn't know where it came from before. So that was pretty cool. Some other things, a little more recent things. We just made this announcement this summer. There's something called intermediate mass black holes. That's what I alluded to before, where there are certain masses that we can't form through a single star, a certain mass of black hole. So in this case, it's about 65 to 135 solar mass black holes that we know we can't, at least in the universe that we can observe, we can't make stars that are big enough that at the end of their life would turn into something like this. And so this event, GW 231123, the designation here is the date. So this would be November 23rd of 2023 is when this event occurred. And it had components of 103 and 137 times the mass of the sun. So in this kind of range, like, where does this thing come from? We can't make stars that are big enough to generate something like that. And the final mass was 225 times the mass of the sun. So that was probably that big blue blob that I showed in the masses of the stellar graveyard chart. That was that one right on the far right-hand side. And some other kind of cool things came out of this. We could determine that these objects were also spinning. So you can read about more of this and the press releases and the stories we've written on our website, and I encourage you to do so because this is just a snapshot, some nice graphics that people made. More in that kind of realm of these intermediate mass black holes that LIGO seems to be detecting a lot of. We've had a couple of those. Another one that was, you know, the resultant mass was 173 times the mass of the sun, 147 times the mass of the sun. So it does suggest that there is this so-called hierarchical formation of larger mass black holes. So, you know, pairs of stars, these are objects that are, you know, not just pairs of stars, but they're in clusters of massive stars that are, you know, one after another turning into black holes, and they're gravitationally bound to one another, and they just keep smashing into each other and making bigger and bigger black holes. So this is, you know, another way that LIGO is contributing to our understanding, not necessarily even of just black holes, but of stellar evolution as well. And then there are these things called the mass gap. And that's what we saw that in the very beginning too, in the masses in the stellar graveyard, where there are, you know, all these neutron stars are kind of down here. These are objects that are, they're not black holes, but they're kind of stars that are made of almost entirely just neutrons. So they're just like giant atomic nuclei. So you need a star between 10 and last I looked, you know, something like 25 times the mass of our own sun at the end of its life will likely turn into a neutron star down here. Much heavier stars, much more massive stars will turn into black holes. But when astronomers were first observing neutron stars and black holes, there was kind of this region of masses. Again, this is masses on the vertical scale here, solar masses. There was this gap here where they weren't really observing anything between about 2.5 and 5 times the mass of the sun. They weren't seeing neutron stars. They weren't seeing black holes. And so that became known as something called the mass gap. It's like, why are we not seeing these objects? Are they not there? Do they not exist? Can you just not observe them in electromagnetic waves? You know, what's going on? LIGO was starting to see objects in this region. So in my kind of breakdown of the objects that we've seen, where I said there's some question marks about things, some of them are in this mass gap. We don't know what's in here because we can't see it with any kind of light. When we detect something in here, we don't know if it's a really heavy neutron star or if it's a really light black hole. And that is still a mystery to be solved. So I guess one of the, this one here, 230529, so May 29th of 2023, there was this object here, this pink X. And, you know, the two objects that collided were 1.4 and 3.6 times the mass of the sun. Classic example, in each of those cases, we don't know what these things were, you know, were they neutron stars or were they black holes? We don't have any way of really determining that yet. You know, hopefully if at some point there's another detection with some light or electromagnetic radiation that can shed light, no pun intended, on that, we might be able to characterize what some of these other things are. But this is just kind of a handful of some of the cool things that LIGO has been observing. There are all kinds of ways that you can kind of keep on top of what we're finding. And I will share all of these with the club, of course, so that you can, this can be clickable. You can look at these. There's something called GraceDB, which is, you know, the kind of current list of, you know, as it happens daily of possible detections. There's something called the Gravitational-wave Open Science Center. They have a little bit more sophisticated interface, but same type of data. You can see what's published. You can actually get an app on your phone, actually. I think it's still just on iPhone. There was an Android app that they're still working on. It was kind of, I don't know, there was something wrong with it and they were fixing it. So I haven't checked to see if that's up yet. But you can get alerts just the same time that we get them. We make our kind of candidate detections public immediately. What we don't make all of the data for those things fully public, though. We have a collaboration of scientists around the world that get kind of their, you know, first crack at the data. But there is certainly, you will get an alert the same time. Within 10 minutes of something arriving here, you might get a ping on your phone that says, hey, LIGO just detected a gravitational wave. So that's kind of fun if that's something you're interested in. The interactive plots, like the masses in the stellar graveyard, those are really fun to play with. There's different ways to manipulate them and look at them in different ways. Cardiff makes these beautiful sky maps, and I like the black versions of them because they look like beautiful star charts. Lots of great YouTube content that we generate. And of course, we're always happy to answer questions at LIGO. We have kind of introduced the world to a completely new science over the last 10 years, and we've learned a lot ourselves about how to share this with people. And so we are thrilled when people ask us questions, because we just, we're figuring it out on our own as we go. So please ask us questions. You can, oddly enough, I didn't include our website here. I can send that along if you don't know. It's ligo.caltech.edu, but you can reach out to any of our outreach team. There's a link on those that you can send your questions, and we are more than happy to find an answer for you. So I think that's my whirlwind introduction to LIGO.
Well, thank you very much. We appreciate the presentation.
Thank you. So I can take questions now, and then we will move into the control room, and we're going to have a little tour of the control room while we're here.
Questions? Somebody's going to have a yes, please.
You mentioned earlier that there was a lot of energy released when I think two black holes collided. Is there any way in the future we might be able to harness that energy for planet Earth?
Unfortunately not. What we're detecting here, the effect that they have on us is so small that, you have that, it's that amount of energy at the source, and then you imagine you're spreading that out. It's like having, paint and spreading paint out over this whole size of the universe, over 1 billion years. So, yeah, not something that we can harness as an energy source here, unfortunately. You would have to be pretty close to one to kind of physically feel it, which is something that would happen, as I've heard in the past. I don't know, it depends on the scale of the event, but if you were, close enough to one of these events, you would hear a pop in your ear, because the waves actually are emitted in what we call the audio band. If you're thinking just about like frequency of wave vibration, regardless of the type of wave, the waves are actually in what we call the audio band. So we have converted our signals into something called a chirp, which is an audio signal. Obviously we're not detecting sound through space, but we can convert the waveform that we sense into a signal that you can hear, because the waves are actually vibrating in a frequency that would be audible to human ears if it were a sound wave. But yeah, other than that, no hope for energy source, unfortunately.
Any other questions?
Yeah. Any other questions? Oh, I will.
Do you have any questions, John?
Oh, I do.
Okay.
Over here's got one.
Okay, please. Go ahead.
Going back off of that, is there like a consistent ratio of energy that's lost each time, or is it like random, like you can't predict how much energy would be lost?
Can you hear the question?
No, could you repeat it, please?
Could you speak loudly, please?
Is there like a consistent amount of energy that's like lost each time, or like a consistent ratio, or is it random, like you wouldn't be able to predict it if you had to?
You mean the energy that's emitted from these events?
Yeah.
Yeah, they're each of them, they're unique. So the prediction is what the wave signal looks like. That's what we can predict. I suppose, in a way, if we're doing that, then we know what the masses of these things are, because that dictates what the shape of the wave is. And so when we know that, then you can use the equations of relativity to, like, literally the E equals mc squared equation, you can use to calculate how much energy is generated. But that's kind of after the fact. But the prediction side of it is our template bank, but we just we're not looking, we're not using the energy factor as something that we look for. We look for the shape of the wave rather than, the energy that's generated after the fact. But it's in there. It would be calculable for sure.
Great questions.
So I have a question. Well, I have a question. So really, what you're looking at, and I'm profoundly ignorant of it, so excuse me, but is the degree of interference between two waveforms. And you're picking that up as points, aren't you? So you're really plotting it, not a continuous sine wave that's moving, right? So you're picking up interference, a little bit of interference, great interference. Is that what we're looking at? And does it occur in a series? Like if I drop a stone in a pond, it's not just one wave. I think we just think so much that there's just one gravitational wave that sweeps through, but isn't this just sort of reverberating?
Yes, I think I know what you're saying. Yes, so the waves, yeah, you imagine like a buoy on the water, right? And a boat goes by and it bobs up and down for as long as the wave is passing. Our arms will oscillate back and forth for the duration of the wave, as long as we can sense it. It's kind of like, our hearing range, human hearing range has limitations. Our instrument is the same way, and it was designed deliberately to be able to sense the mergers of black holes. This all came out of, all of the planning for this came out of theoretical astrophysics and, the equations of general relativity and, the energy what does the instrument have to look like for us to detect these things that we are pretty sure are out there? We don't know for sure, but we're pretty sure are out there. So we have these kind of, limitations in our our detection range. I always say hearing range because it's kind of analogous to human hearing. And so, yeah, as the way the objects are orbiting each other, they're constantly giving off gravitational waves. It's only when the waves, kind of increase in amplitude and frequency that they enter our sensitivity range that we can sense it. And then it kind of sweeps through our detector as the wave passes, as long as it's big enough for us to sense it, just like as long as the sound is loud enough for us to hear it, we're gonna make that detection. So I don't think it's necessarily, it's not like a discrete, blips here and there that we build up a waveform. It's a constant flow of like a continuous waveform that's coming out.
I'm just trying to put my handle on it. If I take a guitar string and I go like that, I will get a wave pattern. However, you're just picking up those moments when you get the feedback that shows the interference pattern, the increasing and decreasing interference pattern. So that's you're actually plotting those moments, and you get the wave. I assume, as opposed to a continuous. Well, let me not, because I'm going somewhere with it. You spotted an actual object, and you did it because you saw these gravitational waves and you had gamma rays. And so you had this great combination and you were able to pick out, locate an object. Could you have done that with only the gravitational wave?
Not yet.
Okay.
Yeah, not yet. So we use basically like triangulation of, that's why we need more and more detectors around the world, because we each, it's like triangulating your cell phone using a couple of cell phone towers. It's really the time of arrival of the signal and then the properties of the signal that give us some kind of sky localization. With two detectors, the best we can do is kind of a banana shape, like we call it the banana shape. Because we don't, the waves could be coming from any direction, from beneath us, from above us, from, whatever. And you know, it helps that the Earth is a sphere. So the Livingston Observatory is at a slightly different orientation than we are. That gives us a little bit more information. It helps to kind of localize things a bit better. We do want to build, there's going to be a third LIGO detector in India. So with 3 detectors, the more detectors we have, the better we can kind of localize the source. But ultimately, we want to be able to localize the source so that our EM partners can then go point their telescopes and see if they see something. Because by their nature, gravitational waves are, you know, invisible. We sense them. We can kind of say they came from that part of sky. But in terms of, and, you know, maybe we know, okay, it's a couple of black holes that smashed into each other. By their nature, merging black holes are not going to emit light because there's nothing there to emit. You know, if maybe another star or some other object were involved, maybe it would give off some, you know, a flash of gamma rays or something as well. There may be something like that. And there are limits to how far away we could detect those types of events too, because of the nature of light and how quickly light kind of dissipates through the universe. There are limits to how far away we would still be able to, you know, astronomers would be able to see an event that you know, like another neutron star merger, or so even if we can tell the astronomers where to look, they still may not be able to see something.
I see. Thanks, Kimberly.
Does that make sense?
Yes.
Yes.
Okay.
Any other questions? Yes, please.
So you briefly touched on it earlier, but how do you prevent such a sensitive instrument from picking up noise from just something like the electronics in a wall or anything like that?
Yeah, we let's see. Am I still screen sharing here?
Yes.
Okay, do you see this thing called the quad suspension?
Yeah, just hit the play button so we can see that.
Okay. There. Got it?
There you go. Perfect.
Okay. So this is kind of the final stage in how we isolate the mirror. So we call this the test mass. It's the mirror that reflects the laser beam. This is kind of the last well, let me get my pointer here. You probably can't see that. This down here, this is what lives at the end station. So the very end of each arm, there's a structure like this. This is covered over here. It has a cover on it, so it doesn't normally look like this. It looks like this beautiful piece of glass. This is the last kind of way that we isolate this mirror. This is the thing that we want to imagine, you know, feel like it's floating in space. All of the stuff that comes above it, and it's also surrounded by more stuff, is designed to absorb and cancel out every vibration we possibly can think of, like physical vibration of the Earth, including the tides. So in this picture over here, we call it a quad suspension because you see it's actually attached to this platform up here. And the mirrors are this mirror here is suspended by glass on glass fibers. There are 4, we call it a quad suspension. It's basically a 4-link pendulum. And if you've ever played with the pendulum, every time you add another link in the chain of the pendulum, it doesn't matter how much you shake the top, the bottom is not going to shake so much. And so that's just kind of a basic kind of Newtonian principle of pendula. So in this case, this structure, I'll kind of back up to the macro structure and then I'll come back to this one. This structure lives within a much larger structure that's called our active isolation system. And that means we have, I don't know how many, 2 dozen seismometers around the site here that are constantly picking up, you know, different frequencies of vibrations from the Earth. That gets fed into a computer that creates a feedback mechanism. So kind of like noise canceling headphones. And so we can physically move this active isolation structure that this thing is suspended from to counteract those big vibrations. And that actually includes things like the moon, the tides, because, you know, the moon is constantly moving, the tides are always moving. And we're so sensitive that the tug of gravity from the moon can like move our buildings around and our structures around enough that it can think that we're sensing something or cause one of our seismometers to think that we're sensing something. So lots of feedback mechanisms go into just kind of the outside of this structure. And so that gets rid of like big things like earthquakes. We can physically counteract the earthquake. We sense it with our seismometer. We send the signal to a computer. The computer then sends a vibration signal into this big macro structure to counteract that vibration. That's kind of the concept of the noise canceling headphone. I don't know the numbers off the top of my head right now of how many kind of so-called channels of vibration isolate. It's thousands, basically. And so, but that's only part of the story. So we can get rid of earthquakes and wind and trucks and people and, traffic and other things going on, big earth things going on. Inevitably, some of those vibrations still make it through into this final stage, this quad suspension. And so this thing, these 4 links in the chain, there's one here, there's one here, there's one here to this, what's called the penultimate mass. And then the final bit down here, whatever leaks through in the top that we haven't successfully canceled out actively gets taken care of in this, what we call a passive isolation system. And it's called passive because largely we're using these principles of a pendulum to just cancel out, each link in this chain absorbs vibration from above and prevents it from reaching the next part down below. There's a few more sophisticated things going on here in some of the materials we use, but this, just in this section alone, and this is probably, by the way, you can see one of these in the Smithsonian. It's now in the Smithsonian. Our quad suspension that came from the Hanford Observatory is now on display in the Smithsonian, heads up. It's like 100 million times more vibration isolation happens just in this structure, from this top level to where the mirror resides here. So any little vibration that leaks through from the external environment that touches this plate up here is reduced a further 100 million times before it reaches the mirror. And that's done through, largely the principles of pendulums. The mirrors weigh 40 kilos each, so they're really massive. So just by inertia, they don't want to move. And so we take advantage of that. This whole system, the active and the passive system, is so successful that we then had to deal with kind of quantum effects. We're now dealing with quantum effects. We have to manipulate our laser beam because we're sensitive enough to pick up quantum variations in the photons in our laser beam that are now a source of noise to us. And so some really amazing people at MIT created something called a quantum squeezer, which I cannot explain. It's one of those things, there's a lot of hand waving that happens. But because of the success of this kind of physical vibration isolation stuff, we're also now confronted with, either the vibrations of the coatings on our mirrors. The mirrors are coated with something like 13 layers of coatings that make them really super, almost perfect reflectors to our laser beam. But then coatings are made up of, molecules that like to vibrate when they're heated up by a laser beam. And so that becomes a source of noise. And so coatings in material science are a big part of what we do to help isolate, by any type of vibration. And now we use this quantum squeezing device that we can kind of play with the laws of quantum mechanics to make our laser even cleaner, the properties of the laser cleaner, so that we kind of eliminate some noise that is intrinsic to the laser beam itself. So there are like thousands of layers of feedback mechanisms that happen between this kind of macro outside thing where we're pushing this giant structure around to, cancel when they're harvesting the wheat down the road, down to manipulating the quantum state of photons in our laser beam. So it's kind of mind-boggling what we can achieve.
It's incredible. Any other questions?
Did that answer your question?
Yes.
It
Okay.
did. I just have a small follow-up. Is the laser suspended in a similar fashion, or is the laser fixed in position?
Good question. The laser is actually, it's on a table. It's a big giant table, so it's fixed. It's also not in vacuum. The other thing I didn't mention, kind of in the beginning, we operate in a vacuum system. We are the world's 3rd largest vacuum system and the world's 2nd cleanest vacuum system, after the CERN Super Collider. And we need to do that because, you know, any molecule that the laser beam reflects off of becomes a source of noise for us. It can deflect, it can reflect, it can refract a bit of, you know, it can scatter, and that creates a signal too. So that's why we need to operate in a vacuum. But the laser itself is not in vacuum. It's in its own special room. And we, you know, have special optics that are highly transparent to the laser beam so that we can, as we say, inject the laser into the arms. But the laser, it's interesting because after we made our first detection, I think, when we made our announcement, the laser does sit on a really stable platform. So the laser table itself has to be somewhat isolated from vibrations, obviously. I don't know, like, all the technology we use for that. It's not that sophisticated, but I know that after we made our announcement of our first detection, we were approached by some people in tech and industry asking us, how do you stabilize your laser? How do you isolate your laser from vibration? So that's kind of one of the spin-offs that, you know, we've been able to contribute to other industries who use lasers in manufacturing or for other purposes. But yeah, the laser is not suspended, it's on a table, but it is somewhat isolated from vibration.
Okay. Any other questions? No further questions. Were you going to show the control room real quick?
Yes, let's get over there. So I guess I'm not sure what you are seeing. You're seeing my screen, right?
Yes.
Okay.
I see,
So
I see the presentation and your video.
Okay, so I'm going to walk over to the control room. Okay. Now, we practiced this earlier, so hopefully this will work. TJ, our operator's laughing. Okay, I have so I guess if I share, I have to share that. Do I stop sharing? Yes. I'm gonna stop sharing and then we'll see how we.
Yep.
Okay, right. And then I choose
The other camera.
the other camera. ETZ.
There we go.
Oh, you see it?
Yes.
Oh, excellent. 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 Okay, so I just walked into the control room here in LIGO. I just walked across the hallway. I have a little remote camera here. First of all, you see down here, wait, this is TJ. TJ, I'm gonna zoom in on you. You should see the acrobatics I'm performing right now. They're waving at you, TJ. You wanna wave back? Yeah, there, TJ's gonna wave back. I can zoom in some more. Can I zoom in? Why is it zooming out? Because I'm hitting the zoom out button. Here we go. So, you know, I mentioned when we are operating 24 hours a day when we're in an observing mode, 7 days a week, which means we need someone to kind of babysit. That's a terrible term, I'm sure. They say it all the time. Okay. But this is TJ. He's the operator on duty this evening. Hello.
Hello, TJ.
Hey. So TJ's job and the operator's job is to make sure that the instrument stays what we call locked, which means in an observing state, in a state where it can actually sense gravitational waves at all times. There are lots of things that can knock us out of lock. For example, there was an earthquake a couple of hours ago in Oregon, which knocked us out of lock for a little bit, but TJ managed to get that under control. So yeah, some people ask, can we predict earthquakes? We can't predict earthquakes. We are susceptible to earthquakes like everyone else is. If it's something that's really, really big and could damage the instrument, we have ways of kind of protecting the, you know, the optics, the expensive mirrors and things, so that if something, you know, if one of our fibers breaks that suspends the mirrors, it's kind of, you know, it'll kind of hold it there. It won't break the whole instrument because those things are kind of expensive. So, you know, we're operating 24 hours a day, 7 days a week. It used to be that there had to be someone in that chair where TJ is sitting, even overnight. But a couple of years ago, they kind of finalized a system that enables the operator who's got the overnight shift to monitor the instrument from home. So if the instrument goes offline or, you know, loses lock, they can kind of get it back online from home. So they don't have to be on site anymore, which is nice for them. TJ is going to be here until 10 o'clock tonight. So that's the shift. And then the next person will take over until, you know, 10 to 6 a.m. Do you do 10 hours? What are your 8-hour shifts, I guess?
The overnight thing just goes till 7:30.
Overnight goes to 7:30. So that's TJ, the station. He is now also looking at all of these monitors. I'll just kind of pan around so you can see the types of things that all of this stuff. So some of these, like this one on the very left side here, not sure I can zoom in so well. This guy here. This one is kind of giving us an estimate of how sensitive our instrument is at the moment. And not sure we have this online anywhere. It would be nice if we had a version of this online. But I keep pushing the zoom button. I guess I've reached the, no, maybe more. So the blue, you see this kind of blue squiggly line, that's the signal from here, from Hanford Observatory. The red squiggly line is the signal from our Livingston Observatory. And there is a purple line, I think, is Virgo online right now? I can't see.
Virgo is online, we just don't have it up there.
Oh, okay.
Because it's shooting issues.
Okay. Normally there's also the Virgo, the Italian detector. We see their signal on here as well. This vertical scale here, I don't know if you can read it on your end, but this is a distance scale. And it gives us a sense of how far away our instrument could detect a couple of neutron stars smashing into each other. We use that as kind of it's like a baseline, because astronomers have known for, you know, decades that binary neutron stars exist. We know a lot more of their properties, you know, we know the types of, we know their masses, they're kind of narrowly defined masses. And so they're also kind of the, other than something like a supernova, which we haven't detected yet, they're kind of the least powerful type of object or event that we could detect. So we know if we can sense at least some neutron stars here, black holes generate much more powerful gravitational waves from across the universe. So this just gives us a good kind of baseline to assess how well our instrument is doing. I guess it's been kind of windy, you know, here in the Tri-Cities. That's why you get this wavy line versus Livingston. It's a little more of a straight line. The top is a zoomed in version of what you see at the bottom, by the way. So it looks a little bit more dodgy. And I guess, yeah, a couple hours ago here where it dropped out, that's where we lost the lock. And then there was the earthquake and we got that back. So yeah, this is just, you know, there's nothing, this is just a way that we can kind of see, oh, how well were we doing? And typically we're up at around 150, 160 megaparsecs. So like 500 million light years away. So in theory, we could potentially detect a couple of neutron stars merging if they were within 500 or 600 million light years of Earth. And again, black holes are much more powerful. We can detect them from much farther away. So that's what that shows. And what it shows, actually, I also will point out from right to left in this direction, this is the current moment. And so it constantly scrolls off to the left. So you can see the last 24 hours. This is a 24-hour scale here. So yeah, you can see Livingston was kind of operating in times when we were not, and vice versa. Let's see. Zoom over to something else. Or pan over. This one here, this is kind of an important one. And I was talking about how the waves are different frequencies. That's kind of what this chart or this graph shows. And when we are, what you need to know about this graph is the lower the red line, the better. So on the left-hand side, this kind of y-axis, this is giving us a sense of how much vibration we're sensing, you know, between, you know, how much motion is occurring in the arms. And so you see on the left-hand side, and on the bottom is the frequency. So frequency like sound, you know, low frequency to high frequency. The low frequency on the left, you see the lower the red line, the more sensitive we are to those frequencies. So you see at these low frequencies, we're less sensitive because the line is higher, which means there's a lot more kind of noise. We can't sense a motion that's of these teeny tiny scales that you see on the left-hand side. And so this is kind of a typical shape of what our sensitivity curve, you know, looks like. You see a bunch of these like spikes here. Some of these red ones are really interesting because kind of off to the right-hand side, they get kind of closer and closer together. These spikes are called violin modes, and these are inherent to the glass fibers that are actually suspending our mirrors. And, you know, I talked about the different types of vibrations that we have to deal with beyond the physical stuff, the earth stuff, but things that are inherent to our materials. This is one of those cases where the molecules, the fibers themselves, the glass fibers themselves, just naturally vibrate in these multiple frequencies, but there are these very kind of discrete lines here. And so they're something called violin modes because they're kind of overtones of different frequencies. We can't do anything about these. These are just part of the nature of the materials that we use. There's a lot of other vibration, you know, every different frequency has kind of a different sensitivity level. So you have to kind of imagine it kind of averaging out over the end, over the end here, or over the whole thing. The green ones on this side, these are something called like calibration lines. So we have to know that what we're measuring is actually what we're measuring. And so we can put in kind of certain signals at different frequencies. So we know the vibration, for example, that we're injecting, that we're kind of causing at some of these frequencies. So we can measure that. We put that in, we know exactly what that is. We look at how the instrument responds. We look at this graph and we see, you know, where is that response? And then we can be sure that, okay, we're seeing that spike where it should be. And that's how we kind of confirm for ourselves that what we're seeing is, you know, what we're seeing in the kind of signal that we're getting is like an accurate measure of what's out there. That's a little more, you know, on the complicated side, but yeah, all you need to know is the lower this red line, the better. Previous observing runs, you know, the red line would have been higher. And so the lower the line, the more sensitive we are to gravitational waves.
Kimberly, we need to wrap up soon.
Okay, I guess that was a good one. I'll just do the one, I'll show you the earthquake because that's kind of fun. This will be the last one. So see that little spike there on the right-hand side?
Yes.
Yeah, that was the earthquake. So we sense these with our seismometers around the site. The other thing that's interesting is so there's the top line that says earthquakes, wind tilting buildings. I mentioned that. And then we have below that the wave-driven microseismic peak. You know, we are also sensitive to storms off of the Pacific Ocean. So you have, if there's a storm system, that's what all of these kind of, you know, that's what this is sensing. And it's just a different frequency of signal that we're getting from our seismometers. But you can see because this earthquake was in Oregon, there was actually a spike in the frequency of that microseismic, what we call microseismic peak as well. So
is that a clock on the very top?
yes. Oh yes. Let's talk about the clock.
How accurate? I mean, you pan over to that. Let's wrap up on that.
Okay, there we go. Any guesses in the room what this green clock is? It appears to be ticking over at seconds. What was that guess?
Somebody said epoch. Epoch.
Oh, I'm sorry, I didn't hear that.
There's a thing in computer science called the units epoch, which is number of seconds since 1970.
Oh,
Looks like that.
almost, it is GPS time. So maybe that's, I don't know if that's what you're
Ah.
thinking. Yeah,
Oh,
it's the
okay.
number of seconds elapsed since the GPS satellite system was turned on in January of 1980.
So similar to.
Wow.
Yeah, yeah.
Amazing.
And we use that because, you know, I mentioned earlier that we need to compare the time of arrival of signals. And so this is a universal timestamp that people around the world can use. So we use this to you know, indicate when a detection comes in. And it's the same around the world. Everybody would have the exact same number. So we don't have to worry about time
Oh,
zones
wow.
or time shifts or anything like that. And so
Perfect.
that's really critical to us making detections.
That's great.
So
Did you
yeah, there
flip,
you
did you flip back to your video so we can see or say goodbye?
Sure. Integrated webcam.
There you are. Let
Here we
me,
are. Bigger view of the control room.
yeah. Do you have enough monitors?
Yeah, just a few. There's more off to the right here that you can't see. So
Yeah.
that's kind of the environmental stuff, wind and earthquakes and that kind of thing.
So let me thank you. This was hugely informative. A ton of information. The amount of science that you're doing there is absolutely incredible. It's mind-boggling to say the least.
Yeah, it really is.
We very much appreciate your presentation tonight. And we thank you very much. Can we have another round of applause?
Thank you for having me.
Thank you,
And,
Kimberly.
I will, I can send you the whole slide set if you're interested, and it has all the links and things in it, so you can share
Oh,
that.
that'd be
with
great. We
Yeah.
could put that on our website.
Yeah, especially our news. We've published a bunch of news, kind of interesting news items lately. So, you know, there's one thing that we published that's a detection that we made in January of this year. So it was a really kind of quick turnaround time. Normally we don't announce those types of detections so soon. So that's kind of fun to read about, but that's on our website.
Awesome. All right. Well, thank you again. Have a very good night. Thank
Bye.
you. Night. Everybody says goodbye. I will end the Zoom course here.
Okay.
Good night. Thank you very
Good
much,
night.
Kimberly.
Thanks. I'll talk to you later.
Bye-bye.